giving a detail of the architecture they used. So yeah, the test, if you look, the test risk never violates the risk bound that was output during the algorithm. I don't think it actually violates the desired risk, but yeah, the risk bound is the thing that gets output at the end of your the algorithm proposed, the selective SGR algorithm. So they compared this to a baseline where I think what they did was they maximized their coverage while keeping the training error less than the risk. So I think they just kept changing the threshold until they can get as many samples without violating the risk constraint. But then at test time, this violated the bound 50% of the time. So that's just showing that what they propose is not just some overkill, I guess. It's actually useful. So yeah, and then just going through the different results for each one. So I think the last paragraph kind of just in the conclusion, it's kind of it's kind of suggesting that this was kind of a first step, but the best way to go about this problem would be to train F and G simultaneously to get the optimal coverage. But this is their first step in the direction. And then I think they don't say it explicitly here, but also what we were talking about, using different confidence rate functions. And yeah, that's just another applications in medicine and stuff. But yeah, that's it pretty much. Any comments? Do you want to just wrap that up? Anything you saw about the empirical? If anyone read the paper, or do you want to look at anything specifically? What I found a bit, what I actually was a bit confused about, maybe sort of, is it calls. It says finally we was able to guarantee this method with amazingly small 1% error while covering 78% of the domain. And I think that's referring to this desired risk of 0.01 with the risk bound of effectively 0.01 and 78% coverage. What I don't get about this, the thing that confused me, is why they're referring to it as a percentage error. Like, I thought the risk in these things was considered the selective classification risk. I don't know why the percentage would make sense to me. That part was the only thing that kind of threw me.
I think that they refer to the error as how many times the bound was violated.
Oh,
so
okay.
They performed the experiment many times, and then because it is not clear, but they do say that they did not apply Bonferroni correction, which means that they are running the same experiment many times and then just taking the average result and then comparing the results. So they say that that is the error, 1%. They don't say that it's, like they argue that that's significantly small, like it's significantly below that the average that they show. So if you look at the average of that,
here.
So that is most likely an average risk-bound error.
Yeah.
Test risk.
Yeah, so you're saying it's violated.
And they say it's below 1%, and they say that's significantly relevant. But yeah.
I think I maybe just saw the 1% and I falsely just tried to make sense of the table here, but I don't.
Yeah, that's what's interesting about this algorithm, is that you can both specify the desired risk. So that 1% is what is the probability that my algorithm is not going to give me something with the specifications that I want. And then you can also specify the coverage, and then your sort of cost function is your thresholding function, right?
Yeah.
So that's an interesting property, I think. And something else is that you can play with the risk bound, and you can reach a lot higher accuracies, provided that you don't care that much about the risk, right? I don't know. One might argue that for some applications, maybe not self-driving cars, but for some applications, maybe 6% risk is perfectly fine, and then you can boost your accuracy to 97%.
But yeah, I think like what you said about out of sample.
I mean, yeah, these are all in-sample estimates, like empirical estimates, essentially. Dangerous.
The paper, did they comment at all to what extent the coverage is balanced across classes.
I don't think the data sets are MCR and so on. And they're not highly indexed.
No, what I'm saying about the coverage, as in you accept coverage, is it equally distributed? In other words, are you rejecting the same?
I was thinking about why not have used an unbalanced data set, look at the minority class or rather than
Okay, that's also an interesting question. But my question is, even when you've got a balanced class data set, is your coverage equally distributed? Do they comment on whether or not the coverage is equally distributed across classes?
No, I was actually thinking about this. I don't think they do.
Okay.
I think they just consider it as the coverage is only defined by everything in the feature space, which is X. So yeah, no, they don't comment on that. I was thinking about that too. I don't.
That has to be. I don't know. My intuition is that that has to be taken into account somehow in the risk, because you are including the loss in the risk. So if you have low risk, then presumably you're including many classes in the coverage. Because if you leave a whole class out, then your loss is going to explode.
Yeah.
And then your risk is going to be high, even with high coverage, right?
Yeah.
Intuitive.
Well, it's just intuitive. Like if you're getting most of them right, then you probably are covering most of these. But I think it depends on the coverage, right? Because if you're only getting, depends on if your coverage is not extending to 2 classes, then you can get very high. You can get very low risk on 2 coverage. So if you set your coverage to like let's say 60% or 0.6, then you could get like an almost perfect. You can get if you could just say you could train on only some classes and then your coverage is going to be perfect. Yeah, I think that's something that's considered. Yeah.
How many classes it will cover?
Mm-hmm. Yeah. So I think
Yeah, but then your risk coverage curve would have a step, no? Because there it's continuous.
Mm-hmm. Oh.
If you were leaving a whole class out, as soon as you reach that class, your risk becomes very high because you're misclassifying it, no?
I was talking more in general, but not in terms of these specific results. I'm saying like that is something that you would need to consider, right? Yeah, no, obviously not.
I almost use it to measure how similar two classes are, right? By finding the percentage they appear together in the rejection sample. Then you can use that to do other things.
Class 1, class 2, class MISC.
Yeah. Right.
Yeah, cool. Thank you for coming. You can probably tell I'm not a machine learning engineer, I'm just a software engineer. So thanks for going easy on me. Yeah, and do you want to?
Yeah, thank you very much.